Good evening, everyone, and welcome back to the Fivable CRAM session for AP Calculus. My name is Jamil Siddiqui. This is CRAM session number 4. We're going to be talking about curve sketching. If you guys could just give me some kind of indication that the volume is working okay on the side, I'd appreciate it. But we're going to get started right here. So without any further ado, I'd like to remind you guys that we've got our Fivable weekly stream calendar up on the screen right now. This is where you can catch up on any of your AP subjects every week from now until the exam. These are all set and free for anyone who comes on. Feel free to join in on any of these streams. Announcement that I sent an email out earlier, but I wanted to review with you guys that we're going to be having an overload of AP Calculus CRAM sessions for the next 3 weeks, 3 nights a week. You're going to see us Tuesday nights at 9 o'clock doing AB Calculus, Wednesday nights at 9 o'clock with BC Calculus topics, and Thursday nights at 7 o'clock with a second AB Calculus. And of course, those of you who are in BC, the AB topics are included, so you benefit from all 3 of them. There's a new event going on with Fivable, the Fivable Olympics. These will be beginning in May. Students will earn points for engaging in live streams, replays, slides, study guides, and community forums. It's a competition for you where you can earn points, and there are prizes available. There will be 42 individual winners, 3 team winners, and 1 class winner. Eligible for prizes including scholarships, laptops, food delivery, subscriptions, and more. So please check that out on the Fivable website. Again, the Fivable Olympics, they'll be starting in May. And as always, follow us on all of our social media at ThinkFivable, where we will give you guys the updates on all the different things that are happening. So tonight, we're going to be looking at something I call curve sketching, but I want to be clear about this. We're not actually going to be graphing anything this evening. We're going to be talking about the topics that are related to curve sketching and how they are shown on the AP exam. So we're going to go over some key terms first to make sure that you've got the right vocabulary to follow along. Then we're going to look at the different ways these examples are given on the AP exam. One is examples with explicit functions. Another one is examples involving the fundamental theorem of calculus, and I should follow up on that with you. This is really kind of a 2-part session for AB Calculus. Starting tonight on Tuesday, we'll be continuing on Thursday night. A lot of the fundamental theorem of calculus is involved in the types of examples. So if you follow along tonight, there are some other problems that we'll do on Thursday night that will kind of go along with it. Someone's asking what's an explicit function. An explicit function is when they tell you the function explicitly. In other words, something like f of x equals x squared plus 3x plus 7, where you've actually got the rule for what that function is. That's what's meant by an explicit function. So again, the fundamental theorem of calculus heavily involved, and tonight and Thursday night we'll be following up, okay, with the fundamental theorem. And then also something that some of you have asked about before we started this evening, examples using the graphs of f prime of x, okay? Before I jump into the key terms, just one of the questions, will there be curve sketching on the exam? It is rare where they ask you to actually draw a function on the AP exam. It's far more common for them to ask you for characteristics of the curve, where it's increasing or decreasing. I can't say it never happens. I think it's happened maybe once in the last 10, 15 years, but it's very rare, okay? The only curve sketching that is usually on the exam is in slope fields, when they ask you to draw a solution curve through a slope field, okay? And that's kind of a different example, because in that you're just following the slope field to create the curve itself. This year, I would be surprised if they came with an actual draw a graph, but I'm quite confident that they will be asking us for the different aspects of curve sketching, which we're going to talk about tonight. So some of the terms that you're going to need to know as we talk about this tonight and on Thursday night. Number one is the word increasing. When is a function increasing? And that is basically, you can find out when a function is increasing by checking its derivative and finding out where the derivative is positive or greater than 0. If your slope is positive, your function is going to be increasing. Likewise, a function is decreasing. That's going to mean your slope or your derivative is negative. A critical point. This is a point that exists on the graph, so it has to be in the domain, okay? But it's a point where the derivative is either equal to 0 or undefined, okay? That's going to be your critical point. There are 2 specific types of critical points that we'll be talking about. One is a relative or a local maximum, and that is when you have established that you have a critical point, so your derivative is equal to 0 or undefined, but your derivative is also going to change signs from positive to negative. In other words, your function will be increasing until this point and decreasing after, and that will cause you to have a maximum. Along with a relative or a local maximum, there's the relative or local minimum, which is, again, the same idea. It's going to be a critical point where the derivative is going to change from negative to positive. In other words, this time your function will be decreasing until that point and then increasing afterwards. All of these terms deal directly with the derivative. So if you hear any of these terms, increasing, decreasing, critical points, max and min, you're thinking first derivative for all of these. Then the next set of terms you're going to want to know, again, kind of piggybacking off the idea of a relative maximum, is the idea of an absolute maximum. An absolute maximum is the single greatest output that that function has, okay? A relative maximum is just going to look like a bump. It's where you're going to go up and then you're going to go down. You can have multiple relative maximums on the same graph, but there's only going to be one value that's the highest, and that is going to be the absolute, or sometimes called the global maximum. And likewise, the absolute or global minimum will be the value of the function that is the least, okay? If you've ever spent some time finding absolute maximums or minimums, hopefully you've been introduced to something called the candidates test. And on the AP exam, the easiest way to justify your work, to show your work for an absolute maximum or minimum, is to do something called the candidates test. It's where you do a comparison of all your critical points and your endpoints, and you find the value that is either the highest or the lowest, depending on if you're looking for the absolute maximum or the absolute minimum. In that situation, the candidates test, and we'll actually see an example of this evening, is all the justification you need. There's nothing written, no written sentences that need to be done. It is just the candidates test. I see the question asking it's the same as the first derivative test. It is not. The first derivative test is just finding out where your derivative is changing signs. The candidates test takes that first derivative test and it builds on it. So again, when the time comes, we'll do the example. I'll take any questions you have at that point in time, and we'll look at the candidates test in action. Again, all of the terms so far, all related to the first derivative. The next terms that you want to be familiar with when it comes to graphing functions is concavity, okay? When you're talking about a function being concave up, that means your second derivative is greater than 0, or an alternative way of describing it is when your function is increasing, okay? So, I'm sorry, your derivative is increasing. I misspoke. When your derivative is increasing. So if your slopes are increasing, your function is going to be concave up, okay? Concave down is when your second derivative is negative, or another way of saying that is when your derivative is decreasing, okay? So depending on the example, when you're justifying concavity, you're going to use one of these two examples. If you're talking about the second derivative, you'll say the second derivative is positive or negative for concavity. If they're giving you a derivative, you're going to find out where that derivative is increasing or decreasing. And that will answer the question of concavity in each of these cases. And again, all of these things we'll do through examples as the evening goes on. The inflection point, that is a point that exists. It has to be a point on your graph where the concavity changes, okay? It's kind of like a critical point, but not exactly, because a critical point is a place where the derivative is equal to 0 or undefined. A critical point does not require a sign change. The inflection point is done with the second derivative, and it's where the second derivative equals 0 undefined, but it does require a sign change. So if you do not see a change in signs, then it will not be an inflection point. I'm just reading the questions now. Are there any inflection points that could exist where f double prime does not equal 0? There is a case where the second derivative can be undefined. Your function can exist and be undefined in the second derivative. So again, we're going to see an example of that as we go on this evening. One last thing I want to just throw at you right now is the fundamental theorem of calculus. And here it is stated. You should be familiar, hopefully, with the fundamental theorem of calculus through your calculus classes already this year. It is wound very closely with the types of questions they like to ask. So, like I said, tonight, Thursday night, we're going to follow up both nights by doing some problems with the fundamental theorem of calculus. So you're going to see some similar problems on both of these evenings, reinforcing each other. So tonight, we're going to go at it from the graphical or the graphing standpoint, with just a little bit of emphasis on the fundamental theorem. Thursday, we're going to come back with a strong emphasis on the fundamental theorem. So if you have questions about the fundamental theorem, feel free to ask them this evening. But again, just keep in mind, we're going to come back Thursday and really, really go deep into the fundamental theorem of calculus. Okay. The first problem we're going to do is an example with an explicit function. This is where they're giving us the actual function and the rule that goes along with it. And this problem actually comes from the 2011 AP exam, so somewhat recent, and we're going to take a look at this. So I'm just going to switch over to my tablet right now. If you guys will give me a second. All right. So we're going to look at this question tonight. And again, someone asked earlier what's meant by an explicit function. An explicit function is where they're giving you the actual rule. We can just plug into this function and get answers, okay? So in this problem, they're giving us the derivative, and they're going to ask us some of the questions related to what we saw just a minute ago. In this one, find the x-coordinate of the critical point. So here's our first important key word right here, critical point. So the first thing you need to remember is that a critical point is a point where the derivative is equal to 0 or undefined, okay? So I'm going to kind of reinforce the definitions as we go through. So that is telling us, let's look at where f prime of x equals 0 or is undefined. Now, someone asked on the questions, can we write DNE for does not exist? DNE is perfectly acceptable on the AP exam. Undefined is the same kind of answer. You can write UND for undefined. You can write the word undefined. The readers of the calculus exam will be good with any of those answers. So DNE does not exist written out, undefined, the word written out, or UND for undefined are all perfectly acceptable. Okay. So again, we're asked to find the critical point of f. So to me, that means first derivative right away. I'm looking where the first derivative is equal to 0. Now, before I get too far into this, I just want to point something out. They are telling us that we are only on the domain where x is greater than 0 in this problem. So we are staying on the right side of 0 in this problem, and that's going to limit our domain from 0 to infinity. So just keep that in mind as we go through. But just practicing with the vocabulary, finding the critical point is finding that derivative and setting equal to 0. Our derivative in this problem is 4 minus x, and I'm going to write this as over x cubed because of the negative exponent. And because we want to find out where this is equal to 0, I'm going to start off just by writing this equation. A fraction can only equal 0 if the numerator equals 0. So this is going to turn into 4 minus x equals 0. And pretty quickly, we're going to find out that x is equal to 4 in this case. Okay, so we do have a value of x that leads to a critical value. We should make sure that this value is defined for our function. But if you read, it says the domain is all positive real numbers where x is greater than 0. So we know this is in the domain. So we have a critical point at the x-coordinate x equals 4. Okay, so that's the first part of our answer. Where is there a critical point? What is the x-coordinate of it? Oops. Okay, so from there, we keep reading, and now it's asking about a relative maximum, a relative minimum, or neither. Okay, so I saw some people in the chat session already asking about the first derivative test and what is that compared to the candidates test. Well, this is a perfect example of where we're going to do the first derivative test. The first derivative test says what we want to do is we want to find out where the first derivative is positive and negative. So my way of doing that is what I like to do is I like to use a number line. Some of you guys might use a sign chart. It's all kind of the same idea. I'm going to say, let's take a look at this example and find out where the derivative is positive or negative. I just realized one thing. I took care of the 0 case. I didn't talk about the undefined case. So I'm going to go back there and make sure it's clear why we need to talk about that. This derivative can be undefined. We've got the denominator down here, and that denominator could equal 0. So if we're talking about where this derivative is undefined, that would be like saying, where is the denominator equal to 0 in this case, which would give us x equals 0. But they made it clear that our domain here is for x greater than 0 only. So since our domain is limited to greater than 0, this is just kind of an extraneous answer for this problem. We are not allowed to use the answer x equals 0 because they've specifically told us x has to be greater than 0. So that's why we're not including the x equals 0 in this case. So now I'd like to set up the first derivative test. The way I do that is I use a number line, and I always like to label it with my derivative. So f prime of x is equal to 4 minus x over x cubed. And now what we want to do is we want to take advantage of the idea that there are some endpoints on this problem. So 0 is an endpoint in this problem. We can't include it. It's not included in the example, but it's still the furthest to the left we can go, not including 0. And then we're going to find out all the places where the derivative is equal to 0 or undefined. And the place we found the derivative equal to 0 is 4. So I like to label that just with a z. That's why I'm writing a z underneath it for 0. And now that's it. There are no other places where the derivative is 0 undefined in our domain. I see the comment, should we do a number line or a table? Both are okay. You can do either one. Whichever one you're more comfortable with is fine. I've always used a number line myself. If you've used a table or a sign chart, it's the same information. It works the same way. You'll be fine doing that, okay? So now I know basically that everything between 0 and 4 is going to give me one output for the derivative, either positive or negative. Everything after 4 is going to give me another one. So I'm just going to use a test value I'm going to plug in. So I'll choose a value somewhere between 0 and 4. Maybe I'll choose 1, okay? And when I plug that 1 in, well, f prime of 1, the numerator is positive, 4 minus 1, and the denominator is positive, 1 cubed. So that means we're going to get a positive result here. And now I'm going to go and I'm going to plug in another value greater than 4. So I'll plug it in 5. The numerator in this case is going to be negative because 4 minus 5 is going to be negative. So we're going to have negative in the numerator and 5 cubed is going to be positive in the denominator. So we're going to have a negative situation here. Okay. Can we, again, I'm just kind of looking at the chat. Can we include the extraneous answers on the number line? You can. You can do more work than you have to. That's not going to be an issue. Okay. But one thing you want to be clear about this year is that the exam is in a format where you're given 25 minutes to answer that first question. You're given 15 minutes to answer that second question. When that time is up, that's all you've got. So you really want to be as efficient as you can. So if you can pay attention and notice that, hey, that's extraneous, I don't need it, you're going to save time on that exam. I think that's actually going to be a big benefit to you, especially on this year's exam. From here, the next thing I always like to do is everything in this kind of this bluish color is related to the derivative. But because the derivative is positive from 0 to 4, that means my function is increasing. And because the derivative is negative from 4 to infinity, that means my function is decreasing. So what I always like to do is I like to draw just a really rough sketch of what the function looks like. Because now what you can see, in the region where the derivative is positive, we're saying our function is increasing. In the region where our derivative is negative, we're saying our function is decreasing. That's going back and tying in those terms that we're supposed to be familiar with. Okay. So from here, is this critical point a relative maximum, a relative minimum, or neither? Well, if you look at that graph, and I call this a line graph because it's drawn with straight lines, the line graph very, very clearly is illustrating that we are getting a maximum value here. So the way we would answer this question, find the x-coordinate for the critical point. I just say x equals 0. There's my critical point. Determine whether it's a relative max, min, or neither. I'm going to call this one a relative maximum. And then I'm going to write a very short sentence using my definition. This is a relative maximum because at, and I just realized I wrote x equals 0 there. My mistake, I meant x equals 4 there. Okay. We're calling this relative maximum because at x equals 4, this is a relative maximum because f prime of x changes from positive to negative. That is it. That's what you need to say. Okay. Now I'm getting a question, why wouldn't you call it an absolute maximum? Based on my line graph, this is an absolute maximum, but that is not what they asked. They didn't ask if it was an absolute maximum. So we really just want to focus on answering the question they asked so we don't have to do more work than this is necessary. Okay. So this is a relative maximum. This is where we're stopping on this one. So I hope this is clear to everybody. This idea of this number line right here, you're going to see me use this over and over again this evening. I find it very helpful, and drawing that line graph above it, it's just a nice visual way where I can see this. Question came up about justifying, and let me be really, really very clear about this because the AP exam is extremely strict on this one. tables and number lines are not acceptable justification. Okay, so what I mean by that is this work right here, which I'm about to highlight. Let me highlight it in this color so you guys can see it. This work right here, okay, that work right there, that is not a justification. The readers of the AP exam are actually told to ignore tables and number lines. Okay, that is for the student to understand what is happening in this problem. So that cannot be used as justification. The justification is always going to be going back to the definition. And our definition of a relative maximum that we stated earlier was where the derivative changes from positive to negative. So we've taken the derivative, we've shown the work, and now that's our justification. So do not use a table or a number line as a justification. You will not get full credit for that at all. Okay, so justifications for the most part are just a short written sentence going back to the definitions. So I hope that's clear for everybody. I see a question again about the candidates test. Okay, the candidates test is a justification for absolute maximums, which again, instead of me trying to explain it right now, I'm just going to show it to you when we get to that example. It's one of the examples that's coming up. Okay, so if you just be a little patient, I'll get to the candidates test. Right now, we're just focusing on the relative maximum, relative minimum. Okay, but I will go back to candidates test. Don't worry about that. So in part B of this question, okay, what's the key word we're looking at here? Well, in part B, find the intervals where we are concave down, okay, where F is concave down. So our definition from before, F is concave down. That is another way of saying F double prime of X is less than 0, okay? So our job here is to find the second derivative. We're given F prime of X. F prime of X is 4 minus X times X to the negative 3. So what we want to do is we want to find F double prime of X. So you can do this a couple of different ways. You can do this as it's kind of set up already like a product rule. So I'm just going to set this up as a product rule. So right now I'm just writing my way of doing the product rule. So I'm going to get the derivative of the first times the second, which is negative X to the negative 3. And then it's going to be plus the derivative of the second times the first, which will give me 3x to the negative 4 there. Okay, 3x to the negative 4. Okay, so that's going to be my second derivative. So from here, I just want to clean this up. I always like to have kind of a neat second derivative if I'm going to be working with it. So what I'm going to do here is I'm going to go ahead and I'm going to distribute. So I'm going to get rid of my negative exponent. So I'm actually going to end up with 1 over x cubed. And then I'm going to get plus, but that plus is actually going to turn into a negative because of my 3 out there. Okay, so that's going to turn into negative 3 times x minus 4 all over x to the 4th, which again is negative 1 over x cubed minus 12. Actually, I'm going to go plus minus 12 plus 3x over x to the 4th. So if I go one step further and I get a common denominator on this one, what we're going to end up with is x to the 4th in the denominator, and we're going to end up with, I'm going to multiply that by x over x. So that's going to get me negative x minus 12 plus 3x, which after I simplify this is going to be 2x minus 12 all over x to the 4th. Okay, so there's my second derivative. I'm going to take this second derivative now. I'm going to set the second derivative equal to 0. So 2x minus 12 over x to the 4th equals 0. Again, this can only equal 0 when the numerator is equal to 0. So that's going to take me to 2 times x minus 12 equals 0. After manipulating this a little bit, adding 12 and dividing by 2, I'm going to find out that x is going to be equal to 6. Okay, so we now know that we've got the second derivative equal to 6. But we're looking for concavity. So that means I'm going to have to find out where the second derivative is negative. So again, I'm going to make use of a number line, but this time I'm going to do it for my second derivative, which is 2x minus 12 over x to the 4th. We still have that endpoint of 0 because we've restricted our domain to go no less than 0. And now we're finding that the second derivative is equal to 0 at 6. So I'm just going to test the value before 6 and the value after 6 and find out what we get. When we test the value before 6, pick any number between 0 and 6 and plug it into the second derivative. I'll pick 1. The denominator is going to be positive. The numerator is going to be negative. And when I pick a value greater than 6, any value greater than 6, the denominator is always positive. It's raised to the fourth, and the numerator will be positive as well. Okay. So I saw the question come up: is 6 a potential inflection point? That's a really good question. So I want to stress this. When I find 6 right here, all I know is the second derivative is equal to 0. I don't know if that's an inflection point. The key to the inflection point is, do the signs change? So just finding this value 6, that is not, sorry about that, that is not enough information for me to know whether or not that's an inflection point. But when I go and I make the number line, and now I'm seeing that the second derivative is changing from negative to positive, now I know that 6 would be an inflection point. So it's only after I get down here and make this number line that I can actually state that 6 will be the value where the inflection point exists. Okay? But to answer the question, where is our function concave down? Our function is concave down. So here we go. F of x is concave down on the interval from 0 is less than x is less than 6. It's this region right here where we're concave down. Okay. When you're doing concavity, you never include the endpoints. Concavity is always done on an interval, not at a point. So I don't need equal to. So this is where I'm concave down. And they asked me to justify my answer. All I need to do for a justification here is say, because f double prime of x is less than 0. That's it. Going back to our definition. Okay. So where the second derivative is less than 0, we are concave down. This example, they gave us the function. We were able to use our algebra skills to solve and make use of our number lines. Perfect example of a problem where they give us an explicit function. One last thing I want to point out, not necessary, but it can be helpful in other examples. You're going to remember back here, I made use of this line graph up here, okay? This was a first derivative, so the line graph was of the function. I can actually use that same idea on this number line, but just keep this in mind. Since this is a second derivative, the line graph will actually be of the derivative. So when I draw this line graph, it is decreasing in the first interval and increasing in the second interval. But keep in mind, it is the derivative and not the second derivative or the function. So all I want to point out here is our other definition of concavity, where, let me just highlight this, where the second derivative is negative, the derivative is decreasing. All right, and that's what I'm trying to point out to you from the beginning. Where the second derivative is negative, the derivative is decreasing. Where that second derivative is positive, the derivative is increasing. And that is going to be a key justification for certain problems. Not for this one, but for certain problems. And again, I don't need to use it in this problem because I have the second derivative. I found the second derivative. My definitions and my justifications can be about the second derivative. Question come up: can we draw the number line even though the readers will ignore it? Absolutely, you can. Matter of fact, I strongly encourage you to. Okay, to me, the number line is what makes this problem make sense to me. So you can certainly draw the number line. What I am showing you right here is how I would answer this question on the AP exam, except for I probably wouldn't scrunch it in. I'd give myself a little bit more space than this one screen, but this is exactly the work I would write on the AP exam. So I hope everyone is good with the idea of working with an explicit function. If everything makes sense so far, if you can give me a thumbs up or some feedback, I'd appreciate it. We're about to look at the next type of example where we are not given an explicit function, okay? So for this next example, this time we are given, well, a graph. And this time they're calling it the graph of f, okay? But as we read these questions, you're going to find out that they're asking us about a different function, right? Look in part A, they're asking us about the graph of G. In part B, the graph of G. Again, in part C and in part D, all about the graph of G. So what we need to do is we need to understand how g and f are related. And they've given us that example right here. G of x is an integral of f of t dt from 2 to x. So what I want to do right now is very, very briefly and very quickly introduce the fundamental theorem of calculus. And remember, there's going to be a lot more work done on Thursday night about the fundamental theorem. But what I'm going to show you right now is going to help us to get through these problems this evening. And then we're going to revisit and review some of these problems, not the exact same problems, but the same ideas on Thursday night. So let's just talk fundamental theorem for a second, okay? If I am told that g of x, and I'm going to come down here and write it right here, okay? Actually, I want to give myself a little more space. So let me go down here. If I am told that g of x is equal to the integral from 2 to x of f of t dt, okay? We are asked all the questions about g. We're asked where g is increasing in this problem. So that means we're going to have to find g prime. Okay, if you're asked where g is increasing, we're going to have to find g prime. So we're going to have to take the derivative of this expression that they're giving us right here. We're going to need to find the derivative of that guy. So a lot of people will look at this automatically and say, well, not a big deal. The derivative g of x is easy. The derivative g of x is g prime of x. And I'll agree with you 100%. And then they're going to look at the next part of the expression. They're going to see that integral symbol, and they're going to think, well, the derivative and the integral, those are inverses, so they should probably cancel out some way. Well, here's the deal. I want to be clear. I want to make sure I'm doing this exactly right. So what I'm going to do, instead of just kind of saying they're going to cancel out, is I'm going to actually show these steps. And this is the fundamental theorem at work. So if you'll remember from earlier, the fundamental theorem of calculus states that the integral of a little f function has a name, and we're going to call that guy big F. All right, and this is the antiderivative of little f, okay? This is big F. And the only thing we need to know about big F is big F, when we take his derivative, is equal to little f. And that's the key to understanding this relationship for the fundamental theorem. So if I evaluate this at my top bound and my bottom bound, I now have a new expression. So I'm going to come down here. I'm going to rewrite this the way I like to look at it. I'm going to rewrite it as g of x is equal to, and I'm going to bypass the integral expression completely. And I'm just going to say it's equal to big F of x minus big F of 2. So now when someone says find g prime, I am going to work with this equation right here instead of, I'm going to call this one equation 2, instead of equation 1. Both of them tell me what g of x is equal to. But in equation 2, I'm not fumbling around with the integrals. And therefore, that's going to be a little bit clearer for me. So when I take the derivative of g of x, I'm going to call that g prime. And when I take the derivative of big F of x, well, by definition, we know that big F of x is, the derivative is little f of x. So now, here's a very common mistake, and I want to make sure everybody's clear about this. A very common mistake is to take the derivative of big F of 2 and say it's little f of 2. But I just want to remind you of something. When you write big F of 2, this is a function when you've plugged in a constant. When you find this output, this will be a constant. Whenever you take the derivative of a constant, you're going to get 0. So when I take the derivative of this third thing, I'm actually going to get 0, which means that g prime of x is equal to f of x. Okay, this is an incredibly important relationship in all of these problems. It always works this way when I've got an integral defined function if this bottom bound is a constant, because that guy always goes here in the fundamental theorem, which means it always goes here, which means it always gets a derivative of 0. So as long as that's a constant, it doesn't have to be 2, but as long as that's a constant, it's going to work the same way. And this guy up here has to be our independent variable x. It has to match this guy. Okay, so kind of summarizing this one more time. On any problem where you're given g of x equals the integral from a constant to x of f of t dt, you automatically get for free that g prime of x equals f of x. And to go one step further, if you're talking about concavity in this problem, we're going to want to talk about the second derivative. We can then say that g double prime of x is equal to f prime of x. These three equations go hand in hand, and you will want to use these together all throughout the AP exam. Very, very popular question. I think in the last 10 years, we've seen 8 or 9 of the years have an example very, very similar to this. So again, keep in mind, if you're given an integral defined function, you get these next two for free. And that's going to be the key to doing the problems we're looking at now. So keeping that in mind, let's back up. And let's go back up to part A, okay? We are given this integral defined function again. So whenever we're given that, we know that g prime of x equals f of x. The problem here is saying, where does g have a relative maximum? That's like asking, where is g prime positive? So in this example, they're giving us f, but what you've got to do is you've got to make the link that f is the same as g prime, okay? F is the same as g prime. So my best piece of advice for you on the AP exam, anytime you're given this type of equation, the readers are going to be looking all over the paper to see you write down this expression, g prime of x equals f, because this is the way we're going to take this information about f and give answers about g. It is imperative that you have this statement written on the paper. If you do not have this statement on the paper, you will lose points. So make sure you have it, okay? The readers are specifically told to find that. They call it linkage. Can you link G to F? And if you've got it, you're in great shape. If you leave it out, it's going to really hurt you on the scoring of this problem. So at this point in time, I know I want to find out where G prime is greater than 0. That's what relative minimum, I'm sorry, G prime of X is equal to 0. And then I want to find whether the signs change there. So I'm going to do the exact same thing we did last time. I am going to make a number line. That number line is going to be for G prime of X, but I'm going to be really smart about this and write that that's the same as f of X. And now I am going to put my endpoints on this graph. They start at -4. It ends at 12. So there are my endpoints. Next up, what I'm going to do is I'm going to find all the places where G prime of X equals 0. But remember, that is the same as saying, where does f of X equal 0? F of X is my graph. So really what I'm asking is, where does the graph equal 0? So I'm going to look at the graph. Everywhere I see a 0, that's going to be a critical point. So I've got one here at -2, +2, 6, and 10. All of those places are places where my derivative of G is equal to 0. So I'm putting those on my number line. So -2, +2, 6, and 10. All places where my G prime or my F is equal to 0. Now, I should also find places where G prime or F are undefined, but because this graph of F is continuous, it is defined everywhere. There is no place I have to worry about this being undefined, okay? So now what I want to do is I just need to ask, where is G prime positive or negative? But we're using F as the link, so we're really asking, where is F positive or negative, which really means we're asking, where is the graph positive or negative? So when I look in the region from -4 to -2, that's from here to here, my graph is negative, so G prime is negative. When I look in the next region from -2 to 2, that's from here to here, and then here to here, everywhere there, my graph is positive, so G prime is positive. Because keep in mind, G prime and the graph in this problem are interchangeable. So from 2 to 6, I am going from here to here, and then back down. But again, the entire time, the graph is positive. So I am staying positive everywhere there. And now I'm going to go from 6 to 10, which means I'm looking at this region of the graph from 6 back to 10. But because we're below the axis, the graph is negative. That means G prime is negative. And then in the last region, I am looking again at the graph from 10 to 12. So that's region right here. but we are below the axis, so we are negative in that region. Okay, so based on this, I can now draw a line graph of G. My line graph of G is going to be decreasing, then increasing, and then this is where it gets interesting because I continue to increase, and then at 6 I decrease, and then at 10 I continue to decrease. And this is a line graph of G of x. So the question asked, do we have a relative minimum, maximum, or neither at x equals 10? When I look at 10, I am decreasing before 10, I am decreasing after 10. Therefore, this is neither a relative minimum or maximum. So at x equals 10, there is neither a relative min or max. Now, we've got to justify it. And the way we're going to justify it is because the derivative signs don't change. So we're going to say there is neither because g prime of x, and now here's the really important part, equals f of x. We are justifying this because they give us the graph of f of x, but we are talking about g of x. So you need both. You got to have that link. So because these guys are the same thing, and in both cases, excuse me, because in both cases, for both of these things, g prime of x is less than 0. Okay, for x is between you could say 6 and 12. You could, but it's anywhere between 6 and 12, that entire region. Okay, so I'm going to say for the entire values from x is between 6 and 12. Okay, and because of that, we're always negative, so we do not have a relative maximum or relative minimum, because for the relative maximum, the signs have got to change. Okay, so I hope that is clear. This is, again, another example of the first derivative test. Okay, you could say because there's no change of signs as well. I'm just saying it's always negative. It's the same idea, okay? Both are going to be acceptable. Okay, but the idea is that it doesn't change the signs. And if you do say it doesn't change signs, make sure you use the right function, because g prime of x equals f of x does not change signs. Question on the side. So the whole point of the justification is relate back to definitions mentioned in the questions asked. That is it. That's exactly what it is. You go back to the definition and you use the information they gave you. Okay, so they gave us the graph of f. So notice how everything we do ties back to our definitions and back to the graph of f, because that's the given information. So I hope this one's okay so far. Again, example of the first derivative test. Okay. So the next one I want to do, does the graph of g have a point of inflection at x equals 4? So on this one, okay, key word here, point of inflection. So that means to me, we are looking for where g double prime of x equals 0 or undefined and changes signs. Okay, that's what I'm looking for. Where is g prime, double prime 0 undefined and where is the change signs? Keep in mind, we're still starting with our integral defined function. That means that we get for free that g prime of x equals f of x. And more importantly, in this example, that g double prime of x equals f prime of x. This is going to be the key for this example, because we're talking about inflection points. Inflection points are about second derivatives. So what I want to do now is I want to basically make another number line, but this time I'm making my number line for g double prime of x, which equals f prime of x. Now I want to go one step further with you on this. F prime of x is equal to the slope of f of x, okay? And now I want to go one step further than that. We know in this problem that f of x is actually our graph. Okay, it's our given graph. So whenever we're talking about g double prime, we're really talking about the slope of our given graph. So I'm going to use these two things interchangeably throughout this example to make sure everything makes sense to you, okay? So I want to do a g double prime number line. So I'm going to set this up. I'm going to do g double prime of x right here. I'm going to link it to f prime of x. I'm going to put those endpoints back on here of -4 and 4. And now I'm going to ask, where does g double prime equal 0? And that's another way of saying, where does the slope of our given graph equal 0? Okay. Well, if you look at this example, there is nowhere this graph flattens out. Okay. And thank you. Somebody pointed that out. I'm a little careless there. I appreciate that. That shouldn't be 4 as an endpoint. It should be 12. My mistake. Okay. So that should definitely be 12. So in this problem, we're looking, where is the slope of our given graph equal to 0? A zero slope is a place where our graph flattens out. It's something like that, or it's something like this. There is nowhere in this graph where the slope flattens out. So there's no place where the second derivative is equal to 0. However, it can also be a place where the second derivative is undefined. Now, that would mean where the slope of our given graph is undefined. So some of you guys were making comments earlier this evening about where the derivative can be undefined. The derivative can be undefined anywhere we have a sharp corner. Okay, so as we look at this graph, everywhere I'm highlighting, these are all places where the slope of this graph is undefined. Okay, every single one of those places, because we come to a sharp corner. So now all of these places are numbers that belong on my number line because they're where the second derivative of g, which is the first derivative of f, which is the slope of our graph, is undefined. So the first place we find is at 0, and that's where we're undefined. The next place is at 2. The next place is at 4. And the next place is at 8. Okay. And we got one more at 10. I got to make a longer number line here. Okay, so we got one more at 10. So let me just make that a little bit longer. So again, I am looking for all the places where we have this sharp change in direction on our graph. All right. So in this problem, does the graph have a point of inflection at x equals 4? Justify your answer. Question came up on the side. Very, very valid question. Should we just focus on x equals 4 because of the nature of this year's exam? I agree with that statement. I just want to be clear, you guys are good at answering this in the more general case right now. Okay, so I agree. This year's exam, they asked specifically, they didn't ask where are the inflection points. They asked, is there one at 4? So I agree with that theory as far as this year's exam, but I want to make sure you guys are good at understanding this entire graph. So I'm giving you a little bit of extra information on this problem. So from here, I now want to know, is g double prime positive or negative in this first interval from -4 to 0? Just remember, g double prime always means the slope of our graph. So is the slope of our graph positive or negative right here from -4 to 0? In that region, the slope of our graph is positive. So now I'm going to go to the next one, and I'm going to ask, is the slope of our graph positive or negative from 0 to 2? Well, that's this region right here. The slope of our graph there is negative. The next interval, I'm going to go here, and the slope of our graph in this region is positive, and that's from 2 to 4. Then the next one, I'm going to go from here to here, and that's from 4 to 8, and the slope of our graph is negative. Then the next interval, I'm going from 8 to 10, and the slope of our graph is positive. And the last interval, I'm going from 10 to 12, and the slope of our graph is negative. Okay, so what we're going to see here is that all of these values, 0, 2, 4, 8, and 10, they're all going to be inflection points because we have the second derivative changing signs. So that's the general answer to answer this question specifically. They only asked us about x equals 4. So we would write x equals 4. Well, let me rephrase that. We would write there is an inflection point at x equals 4. And they're going to say justify your answer because, and what I would say is the reason there is an inflection point at x equals 4. Now, you're going to want to say because the second derivative changes signs there. That's what you're going to want to say. But remember what they gave us to work with. They gave us the graph of f. That means our justification has to be about f. So what I'm going to say is there is an inflection point at x equals 4 because f of x, which is equal to g prime, so we're working them both in, is now a place where it changes from, and again, I'm looking at 4 in this case, so I'm going this direction to that direction. So what's happening? F of x, which is equal to g prime, changes from increasing to decreasing. And that is that second definition of concavity, where you're talking about the concavity in terms of the derivative increasing or decreasing, okay? So the more common one is when you're talking about the second derivative being positive or negative, but remember, the derivative increasing and decreasing gives the same information. Because this is a graph of f, and that's equal to g prime, we've got to talk about not g double prime, we've got to talk about g prime in our justifications. And that is key on these explanations on the AP exam. Always justify using what you're given. I was given g prime. I am talking about g prime down here. Okay, so I hope that really makes sense to everybody on this particular example. Part C, find the absolute minimum value and the absolute maximum value. This is going to be a question that is going to spill over into our next Thursday evening probably, but we're going to get it started and do the parts that we can that deal with absolute max. A lot of you guys asked me in the beginning about what do I mean by a candidates test. This is an example that's going to require a candidates test. This is absolute maximum, okay? So the idea is first, who are the potential values that could be an absolute maximum? And the places you're going to find them, the candidates are always the endpoints and the critical points. Okay, these are always the candidates. And when I say critical points here, I really should say, I should be clear on this, I really should say the relative max and the relative mins. If they're neithers, you don't really need to worry about them. It's the relative max and the relative mins. So the idea here is to look at this example and then come up with who are the endpoints and who are the relative max and the relative mins. So if you remember, going back to the earlier part of this example, okay, we already did a first derivative number line. We've got this information right here. Oops. Let me see if I can copy that and bring it to the other one. We've got all of this information right here. Okay, so if we take this and bring it down here, all right, we know who our critical points are just by looking at this. This is where our derivative is equal to 0 and undefined. So how does a candidates test work? Well, here's the idea. You're just going to make a table. You're going to make a little table like this. And I know I said tables were not acceptable for justifications with relative maximums. This is the one place where tables are extremely acceptable, and that's for the critical, for the absolute maximum, the candidates test. So we're going to make a table of all of our candidates and the outputs for those candidates. So our endpoint is at -4, okay? We've got a relative minimum right here at -2, so that's a critical point. We've got another relative maximum at 6, so that is one of the critical points we need to worry about. And we've got another endpoint at 12, okay? I do not have to include 2 or 10 because those are not relative max and mins, okay? So these are our 4 candidates for absolute maximum. Now, I know a lot of you are going to say, hey, there is no way -2 is an absolute maximum because it's a relative minimum. And personally, I agree with you completely. However, if you want to get justification points for a candidates test, you are required to do all critical points. I understand it's not going to win, but that is what they're looking for. So I included on my candidates test, okay? So now the only question I have is, what are the y values for each of these examples, okay? What are the y values? So what we've got to do is we've got to go back and remember that we're given g of x here. So all we've got to do is plug in these 4 values and find out what we get for an answer. So I'm going to start this one by plugging in, I'm actually going to plug in the value of 6 first, okay? So if I want to find g of x, and what I'm going to do now is I'm actually going to take this, and I'm going to get that out of the way so we have a little more space. So I'm going to come up here, and I'm going to start by doing g of 6. So I know I'm not doing the first 2. I'm going to 6 right away, but I'd like to do 6 just because I think that's the easiest one to compute to start with. So the way this function works is when I plug in 6 here, I'm plugging in 6 for the top bound. Okay? So all I'm doing now is I'm looking at this integral from 2 to 6, which means I'm starting at 2, and I am integrating all the way here to 6. So this is a really common question on the AP exam. You're given a graph and you see geometric shapes. Anytime you're given a graph and you see geometric shapes, that is all about using geometry to compute your integrals, okay? In my class, when I'm working with my students, we actually call this the squint test. And we call it that because, if you just kind of squinted at this graph, you could recognize its geometric shapes. And that almost always means you're going to use geometry somewhere to help you integrate. So for this problem, I am going from 2 to 6, which means I'm traveling to the right, okay, from 2 to 6. That makes my dt positive, and I'm above the axis from 2 to 6. That makes my f of t positive. So I know my answer is going to be positive when I integrate this, and it's going to be the area of that triangle, which I just shaded in. Okay, so the base of that triangle goes from 2 to 6. That's a base of 4. And the height of that triangle is also 4. So the output for g of 6 in this case is 8. So I now know that g of 6 is equal to 8. Now, this particular graph, they made it kind of easy on us because it's very, very symmetrical. And what I mean by that is, let's just go back up to the graph for a second. Let me erase this. Let me back up. And let me just look at one half of that triangle, okay? If I talk about this shape right here, that area of that triangle is 4, okay? It is half what we just found. So when we're looking at all these little triangles, they're all worth 4. Everything here is worth 4. From here back is 4. From here is 4. So every one of these triangles has an area of 4. So now the only question is, as you're integrating, should it be assigned a positive value or a negative value? The one that I did first, it went from 2 to 6, which meant I was traveling to the right. That means positive, and we were above the axis. And that is why I got a positive for both of those, which meant that answer for g of 6 was 8. When I go to do g of 12 now, I'm doing the bottom one. I'm going to integrate this from 2 to 12 of f of t dt. I'm going to erase what I have so I can work it out with you as we go. And when I do this one out from 2 to 12, that means I'm going to the right. So that means that's going to be positive going to the right. I am above the axis. So when I do this first triangle, I'm going to get 4. When I do this second triangle, I'm going to get 4. Now I'm going to do this next triangle, okay? But when I do this next triangle, even though I'm still moving to the right, I have dropped below the axis. That means as I integrate this guy, this is going to have a value of negative 4. I hope that is clear to everybody, okay? So we're going to get a value of negative 4 there. This next triangle, again, I'm moving to the right, but I'm still below the axis. That's going to be another negative 4. And this last triangle, so 12, below the axis, moving to the right, going to be negative 4. So as I add up these answers, I'm going to get 4 plus 4, minus 4, minus 4. Those are going to cancel out. And then I'm going to just be left with a result of negative 4. So my output for 12 is negative 4. When I go to do my next value, I'm going to do g of negative 2 in this case. And that's going to be the integral from positive 2 to negative 2. And that's important. F of t dt. When I go to do this one, let me reset my axes here. When I go to do this one, I am now starting at 2, but I am moving to the left. Okay? So as I move to the left, this triangle here is going to be an area of 4, but it's moving to the left and above. Left and above means one positive, one negative. That's going to be negative 4. I'm going to keep going back to negative 2, still moving to the left. That's going to be negative 4, which means when I find my output for this guy, I'm going to get negative 8. Okay, so that should be negative 8 there. Last answer was negative 4. So now I'm going to do my g of 2 of f of t dt. And this time I'm going to plug in -4. That means, again, I'm starting at 2. I'm still going to get this first triangle -4. I'm going to get the second triangle -4. But now when I go to this last triangle, because I'm moving to the left, but I'm also below, that's going to be a +4 in this one. Okay? That's going to be a +4. So that means the answer I'm going to get for this guy is -4. Now, I saw a question pop up about negatives. I'm going to come back to that in just a second. So if you guys let me finish this problem and stay with me, I'll be sure to answer that. But I just want to talk about the candidates test first, and I'll come back to the negative. Once you fill out this table, they've asked me for the absolute minimum value. All I've got to do is just look at the table and pick which answer gives me the absolute minimum. Okay. And they actually ask for both absolute minimum and absolute maximum. So when I look at this, the absolute maximum value is 8. That's the absolute max. The absolute minimum value is, it doesn't matter if you choose it here or here. Oh, I'm sorry, neither of those are the absolute minimum, my mistake. The absolute minimum value is here at -8. So to answer this question, all we've got to do is say the absolute max is when g of 6 equals 8, and the absolute minimum is g of -2 equals -8. If you have this, if you have the candidates test, no other written justification is necessary. This is all you need for your justification. This is the only justification I'm aware of on the AP exam where you don't have to write a sentence. If you do the candidates test and you show that table, that's it. That's all you need. Okay. That is why I am really, really stressing the idea of doing a candidates test and showing all these values. So I hope the candidates test makes sense. Okay. Now I want to go back and we're going to end on this evening. And I just want to talk about the negative sign again on these integrals, because I saw some people asking that question. So let me come back up here. Let me erase. Let me be clear about this. Okay. I'm going to go back and I'm going to talk about doing the integral where we went from 2 to from 2 to -2 of f of t dt. Okay. So this is how I think about it. Okay. This is one way of thinking about it. There's lots of ways to think about it. This is how I always do it. The number one mistake students make when they're doing these geometric problems is keeping the sign straight. Is it positive? Is it negative? So this is how I always handle it. Okay. I look at these two factors, the integrand and the differential. So believe it or not, this dt, it has a sign. It's positive or negative. And I'm going to tell you how you can find out. Okay. So dt, the way you find out the differential is positive or negative is that look at the bounds. If the top bound is greater than the bottom bound, dt is positive. If the top bound is less than the bottom bound, dt is negative. Another way of thinking about that is if you move to the right, dt is positive. If you move to the left, dt is negative. We are going from 2 to -2. We are most definitely moving to the left. I assign dt as a negative in this situation. Okay. So now what about f of t? Well, I'm looking between -2 and 2. F of t is above the axis and above the axis. So that means for this whole region, f of t is positive. That means when I do this integral, these two signs determine my answer. I've got a negative times a positive. This answer is going to be negative. I call this doing a sign analysis. Once you complete your sign analysis, the only thing left to do now is your geometry. Okay. We know this answer is going to be negative. The only question now is what's the geometry? Well, when I go and I shade this in, the geometry of this problem is a triangle. It's 1/2 base times height. The base is from -2 to 2, which is 4, and the height goes up to 4. Therefore, the answer to this problem is going to be 1/2 of 16 and negative, so it's going to be -8. So that's how I got -8 for that answer. Okay. To me, it's about assigning a sign for the differential. Okay. I see a question. 10 does not change signs. Oh, okay, so you go back. I had mentioned candidates are endpoints and critical points. So should it not be all these guys? Okay, so the reason I am not including all the critical points right here is because for a candidates test, you only have to include relative max and mins. Okay, you only have to include relative max and mins. When we got to 10, 10 was a critical point that did not change signs. Therefore, it was not a relative max or min. So you only have to include, I should get rid of this critical point statement. I should just keep it like this, relative max and mins only. Okay, so I just want to do one more example of the geometry to make sure your signs are okay. So if you guys will allow me to do that, I'm going to get a new graph going right here. We're going to, for the time being, just ignore this particular question right here. And we're just going to go back and answer the question, what happens when we find g of negative 4 in this problem? Okay, so as I do g of negative 4 in this one, g of negative 4 is the integral from 2 to negative 4 of f of t dt. I'm going to do my sign analysis again. To me, okay, dt is moving to the left. We're going from 2 to negative 4. So I'm going to make that guy negative, okay, because negative 4 is the top bound. The top bound is less than the bottom bound. To me, that's dt is negative. So now, what's f of t in this region? Well, from 2 going back to negative 2, f of t is positive. But the problem is it crosses over, and it actually becomes negative in this region. So what I'm going to do now is really do a two-sign analysis. For the part I'm labeling as that blue color, I've got a positive f of t and a negative dt. For the part I'm labeling kind of as that gold color, I'm still moving to the left, so dt is negative, and f of t is negative, which means as far as I'm concerned in this problem, I've got two geometric shapes. The first one is going to be negative times positive, so I'm going to get a negative answer for the first piece. And the second answer is going to be a negative times negative, which is going to be a positive answer for the second piece. Once I do these signs, now it is strictly geometry the rest of the way. So for the blue piece, it's half base times height. This was the same triangle we just talked about. It's 4 for the base, 4 for the height. For the gold piece, it's still a triangle. It's 1/2 base times height. The base is 2 and the height is 4. Notice I'm not concerned with the negatives at all. I don't need to do the negatives because I did the sign analysis. All the signs are taken care of from the beginning. So from here, I can just finish this answer and find out that this whole thing is going to equal 1/2 of 16 is 8, and that's negative, plus 1/2 of 8, which is 4. That's positive. So this entire answer would be negative 4. And that's how I got g of negative 4 was equal to negative 4 on the last problem. Okay. It can be really confusing because of the signs, but we're gonna talk about this again on Thursday night. What exactly is dt? I missed it. The whole idea of dt, okay? dt is all about figuring out how you're moving, either left or right, okay? If the top bound is greater than the bottom bound, dt is positive. If the if the top bound is less than the bottom bound, dt is negative. So in other words, if you are moving right, dt is greater than 0. If you're moving left, dt is less than 0. Okay, so I hope that is clear what I mean by dt. Okay. I've got a question from why isn't it 4? I'm not sure what that is related to. I'm not sure what question that is. So if you want to clarify, I'll try to help you out. For g of negative 4, the reason g of negative 4 is not 4 is because of the sign analysis we did here. The bluish triangle is assigned a value of negative 8. Okay. We did the sign analysis right here to show that the blue triangle would be negative 8. The gold triangle is assigned a value of positive. Okay. And by doing the sign analysis first, what that allows me to do is just treat all the rest of the problem like geometry and not worry about the plus or the minus. Okay. You know, you might have learned it that going left is negative and below the axis is negative. If you learned it that way, that would make this gold triangle negative because we're going left and we're below the axis. So two negatives are going to make positive. So I hope that is clear for you guys. We're going to wrap up right now this evening, but keep in mind, we're really just going to pick up right where we left off on these problems on Thursday night with more fundamental theorem of calculus problems. I want to go back and just share a couple more slides with you guys. So if you'll give me a moment. Okay, so a couple more examples. I just want to remind you that calculus, we're on basically Tuesday, Wednesday, and Thursday night, every week until the exam for the next 3 weeks. 9 o'clock today, 9 o'clock Wednesday, 7 o'clock on Thursday. And I'd like to remind you about the Fivable Olympics. If you're interested in that, please go to fivable.me, and then you can sign up on the website there. That is all I've got for this evening. I do see a couple more questions. I will try my best to answer those, but that is all I've got for new information for this evening. So please come back on Thursday night. Any feedback you can give on the side, I'd appreciate it. So if you follow along and things went well, I would appreciate that. I believe the live streams do contribute towards the Olympics. Okay. So one question I got before that: does the problem imply that the domain of G is greater than 2? Does the problem imply that the domain of G is greater than 2? Okay. I'm going to switch back to my tablet for a second so I can answer that a little bit easier. So going back to the original question, okay? Going back to the original question. Does the problem imply that the domain of G is greater than 2? If you look here, it says that for the function G is defined on -4 to 12, okay? This integral does not tell us the domain of G. It doesn't tell us that at all. So X can be values greater than 2 or less than 2 in this problem. As a matter of fact, it very clearly says that we're looking at X values between -4 and 12. So that is not how we interpret this particular example, okay? So I hope that's clear. If you guys have any other questions, I'll stick around for a few minutes. If not, again, any feedback you have, greatly appreciate it, because I'll be working with you guys up until the exam 3 times a week. So I want to make sure that I am being as clear as I can and you guys are getting what you need from me. And again, keep in mind, I'll put this over on the chat. If you have any questions, any follow-up questions, you can reach me at Jamil at Fivable.me. That is my email. You can ask questions. Feel free to send me anything there, and I'll be happy to respond. Anything you need. So related to our streams or anything in general calculus related, I'm happy to help you guys out. So thank you for coming this evening. Again, I'll stick around just for a minute if there's any other questions. Other than that, I'll hopefully see you guys Wednesday and Thursday night this week. All right. So have a great night, and we'll see you soon. Happy to help you guys out. Tomorrow's session, the BC session, it is strictly topics that will show up on the BC exam. It will not show up anywhere on the AB exam. So my advice to you guys who are in AB calculus, really, it's great math. It's a lot of fun, but it has nothing to do with what you guys will be seeing. And I would be shocked if you'd gotten to that in class. It will probably be brand new material, well beyond anything you've talked about this year. So as much as I'd love to have you join us, it would not be beneficial at all for an AB student to show up at the BC streams. You're asking me if I think taking BC Calculus would be a helpful, interesting class. I love BC Calculus. That's my favorite thing to teach. But you're asking someone who loves math. I find BC Calculus to be a great class to tie together everything you learned in AB with a lot of other real life topics and how you can apply it in other places outside of math class. So yeah, I think BC is a great class. The replay of the BC session tomorrow will be available for us to see later for next year. Nikki, I do not know the answer to that question, to be honest with you. I am not sure what will happen with these streams when the school year is over. Email me that at my direct email. I will ask and I will find out and get back to you on that one. Okay, so if you could just remind me by emailing me, I would be happy to look into that for you. Okay, if there are no other questions for this evening, guys, thank you so much. I appreciate your attendance tonight, and then come back on Thursday to pick up where we left off with Fundamental Theorem of Calculus, or tomorrow night if you're in BC Calculus. Okay, have a great night, everybody.